And now we'll switch a bit from the academia to startup, and I want to invite Hadar. Hadar Sharvit is the ML team leader at a startup called Urecsys that will talk about generalized time series model for predicting indoor air quality across diverse building environments.
So hi everyone, my name is Hadar. As I was briefly mentioned, I'm the machine learning team lead at Urecsys. Urecsys is a company that focuses on air pollution and how we can minimize it in indoor environments. Today I will show you work from our team discussing a model to predict indoor air quality across diverse buildings. Starting with what is urban air pollution. So particle matters, nitrogen oxide, and ozone, all of which are diverse sources stemming from transportation and even wildfires that contribute to health risks. Okay, two things you should be taken into consideration is that the fact that these pollution values are for the most part unpredictable and unfilterable, so you cannot filter them using traditional filtration systems some of you may be familiar with in air conditioning. The direct impact is, the outdoor pollution value penetrates to indoor environments. So they highly correlate, and we would like to, the goal of Urecsys is to minimize these values. Discussing about indoor air quality specifically, so three components come to play. First would be the obvious outdoor pollution levels. Those across their diverse sources could be measured using high-frequency sensors that our company scatters throughout large cities and around the world. And the air, the polluted air, is basically fed, the air is feeding into the building using a system called HVACs. Those are like fan-like system that propagates air in and out of the building, which directly impacts the indoor pollution values. Those as well could be measured using high-frequency sensors. Diving into some physical motivation, stemming from differential equations, specifically a very basic mass-balanced linear differential equation that maps the relation between indoor concentration, denoted in C, and the outdoor concentration value. On the left-hand side, you can see the time derivative. Dot is a physics notation for the first time derivative of the indoor source, and how it, on the right-hand side, depends on the difference between the current outdoor concentration and minus the, so basically the entering outdoor concentration minus the leaving indoor concentration in a building or any indoor environment. You could also see that those are factored by some constants that are usually specific to a single buildings. Those could be the airflow rate, these HVAC fan-like system, how they feed air into the building and what's the frequency they're applied with. But also penetration rates and deposition rates that factor out with a unitless amplitude the value of the indoor, the incoming and outgoing pollution. As a linear equation, the solution is provided with two terms. The first would be a constant term, which is pretty much a factor of the outdoor pollution, and as well as the difference term between the previous indoor value, the current outdoor value, factored by an exponential decaying term. So this gives us a nice baseline on which we can at least start and define a model for indoor air quality. So obviously the first approach, we will go over through a few naive modeling. The first would be use the solution I've described just beforehand, but again, as the parameters I've described are specific to a building, you'd have to hard code them specifically using some prior knowledge. You could also use a type of informed model or a physics-informed model where, again, the same simplified physics of the mass balance equation is used, but the parameters that are, for the most part, unknown will be optimized using data from indoor and outdoor sources, sensors, but you would have to account for the fact that optimizing those values might, and you'd end up with non-physical representation of the model itself. And third approach, if you will, would be to discard the simplification assumption and use a deep regression model, the one you like the most, which can complex high complexity dependency that are not represented in the mass balance equation. But of course, you would need a substantial number of samples compared to the other approaches. While those are all are valid approaches, the main con, if you will, is the fact that they generalize poorly on new sites. And this is due to the fact that two proximal buildings differentiate in their indoor air quality based on their unique traits of the buildings themselves. So let's consider a case study. On the right-hand side, you can see two buildings, two clients of ours in Jerusalem with pretty distinct yet similar architecture. And on a test period of aggregated statistics, we can see that the mean indoor value between these two sites differentiate by more than 10%, while still they're being pretty close together, and the outdoor pollution is roughly the same. We can also see that the maximum value of indoor pollution differentiates by almost 30% across the test period. Randomly sampling a window of data, we can see that the peaks tend to be aligned for the most part, but there are indeed peaks in the data observed in the indoor concentration on one side. There are not, there cannot be seen in the other side, and vice versa. This leads me to the fact that some contacts, a differentiating contact that identifies one building from another, should be added into our model. And in a mathematical formulation, transitioning from a probability distribution for a given input X that I will describe in a brief moment, we transition to some context model that takes unique identifiers that could be hard-coded or learned. What might be those differentiating factors? So I think you and I can think of a few factors right off the bat, some of which would be the building size, but also even the number of occupants in the building, and the HVAC, those fan-like structure, the tubes, their lengths, the length of the tube that feeds air from the outdoor to the indoor. All of these are valid factors, but the fact is there are many unknowns, factors that we do not know explicitly. We do not know how to name them, so it would be unfeasible, for the very least, for us to try and use this approach as context. Another approach, which is a different approach to be honest, is to use historical short period of data as context. And what I mean by that in this example you can see perhaps small letters, but we would use a short period of historical cold start data where both the outdoor concentration level and the indoor concentration level will be saved as static context, where the assumption here is that historical values in a cold start period should represent the underlying relation between indoor source and outdoor source. Forgetting for a minute about the context, let's even see how, what is the input and how it propagates through our network. So we have here an example of input data X. We usually take a look back window of roughly a few hours, half an hour to 4 hours tops, where relevant features like the outdoor concentration, in this example nitrogen oxide, and the HVAC system, which can be thought of as like a binary value. Is it open, is it not? But we also use other features like temperature, humidity, etc. And you can see here that the frequency rate is quite high, at least in terms of comparison with other time series modeling. You can then use a backbone of your choice, and in this example we use a basic encoder-decoder sequence-to-sequence model, where a batch of windows is then encoding using some GRU encoder, and the latent representation is weighted using an attention mechanism with the current decoder output. And this backbone alone could be used to predict the indoor value in a single building. But now we have the context. So the context, again, it does not have to be the same size as the input window. But in most of our experiments, we use roughly the same history look-back window, where the features should also include the value from the indoor concentration. So again, predicting for nitrogen oxide, the cold start period will also include the indoor value as a static input to the model. Then again, we would have a distinct, unique backbone. Usually would be a simplified version, a small recurrent neural network, but not only, that learns a context hidden representation. And those are then aggregating using various schemes you're probably familiar with, like a skip connection, where the latent representations would be, their dimension would be matched using a fully connected layer to output the context-aware indoor pollution, or they could be stacked across the features dimension, both of which are parameters we play with. In terms of results, So we can see at the left-hand side a bar plot representing various models we've tested out. The key thing to keep in mind here is that lighter blue represent models that are context aware. So in the training and inference process, these models have seen static information from the cold start period. And where darker bar plots represent models that did not have the context for reference and do not use a static or context backbone when predicting the indoor value. And again, as I've mentioned, we did not lock ourselves to a specific model backbone, both for the context model and for the backbone, the main backbone that takes in the raw input data. So we use a variance of a gated recurrent network with some tweaks noted as temporal pattern attention, gated recurrent networks, as well as sequence-to-sequence with and out attention mechanism, but also transformers with causal and regular attention, which do not inherently outperform recurrent neural networks, as sometimes we became accustomed to. And again, while still preliminary results, we can see that compared to the target indoor value, the lighter blue that represent context-aware model do seem to fit better to the trends and to the overall outline of the indoor concentration compared to models that did not have that context during training, of course, during inference. But again, I would state that the best feature, if you will, of our model is where, again, we've specified 3 approaches for indoor air quality regression models. The first one would still be you'd be using a deep neural network architecture, but now, as we have the context, we may be limiting ourselves as we do need larger amount of data. So all the data that we've aggregated should be combined with a short period of historical data from each of our clients. But the best feature overall would be that a single endpoint or a single model can now rule them all, so we don't have to train a model that is site-specific, which is for the most part unscalable and unfeasible for at least for a small startup. We can just use a single model that was pre-trained, have it hosted on a single endpoint on the cloud, and in the process where a new client onboards, we would only have to ship it to sensors, have a short period of time where we measure the indoor concentration and outdoor concentration, and we can use this static context to provide it with indoor pollution values that could be presented in dashboards and so on. So this is our work, and I would like to thank you for listening. And
do you take into account the temperature and other external conditions?
Yes. So aside from the most crucial factors that are the outdoor value and the HVAC command, we also did features analysis where we end up using both the outdoor temperature and relative humidity, but also the indoor values that, while they do not change drastically indoor in our look-back window, they do tend to allow for better prediction overall.
One last question. I see over there. You have a mic.
I saw you've used an RNN to handle the encoding of the information you received from the static sensing, like the context. Was there any specific reason you decided to choose an RNN?
You're asking whether I wanted to choose a LLM for the...
No, an RNN. I saw you used a recurrent network. Is there any reason you used an RNN rather than something like an LSTM model, which are generally well known to be more resistant to issues?
So RNN is just a keyword for any recurrent model. You can obviously use a gated recurrent network as well as an LSTM. We do not use LSTM. Usually we use a more Usually we use recurrent neural networks with tweaks like I've described before, like a temporal attention mechanisms enforced with the gated recurrent network. But yeah, RNN is just a keyword for the. We also use transformers, but they do not work as well.
Thank you.
Great. So let's thank Hadar again for helping us breathing a better air.